All right. Hello, all. It's the fourth exam. This is one that we have not done an exam review for, and it's entropy. And the one thing I want to talk about when we talk about entropy is we are talking about enthalpy. We're talking about delta S. We're talking about Gibbs free energy. These are all things that determine the disorder of a system. You're working towards something that's going to be working towards disorder because we want to be more disordered. There's things that sometimes confuse us when we think about disorder, in that we don't understand why, say, in ionic solutes, that they become more ordered by water. And then things that are molecular solutes actually become somewhat already less ordered and more ordered later on. We have to think of these things in ways that we would think of something that is moving in a system. Because when I think of water and dissolving, I think, okay, it's becoming more disordered because it's dissolved. But in actuality, it's breaking up, but then it's breaking up and being surrounded by water. And that water is restricting the free ions that we're moving around. So it's just becoming even more restricted. And that's why it becomes a negative delta S. These are things to be thinking of to help make more common sense. Because as much as this feels like common sense, I feel like sometimes it's that whole common sense ain't so common, and that it does need to work through in a system. The one thing that common mistakes I see all the time, combining numbers. Entropy is in joules per Kelvin. Enthalpy and entropy are almost always in kilojoules per mole. Making sure that they're all in kilojoules or all in joules is very important. Another thing is making algebra errors. So many times I see people doing simple math, dividing by 1,000, and it coming out wrong. If you have to put it all in a calculator, do it. But the more important thing is I don't mind mental math, but when you go back through your exam, specifically on calculated questions, when you're calculating something, please double check the numbers, do the simple math, do the simple algebra, because then it saves you from kicking yourself later when you're looking back and you're like, I knew that, I have it right here. The other thing with these is balancing equations, being able to write and balance these reaction equations. A lot of the time people find it hard to combine equations or to create an overall reaction scheme. Be sure to know how to do that, because not only is it going to help you with this exam, like the part 4 part of the exam, but also in parts 1, 2, and 3, aka the 40% before. And finally, confusing standard delta and non-standard delta, G, S, H, etc. Standard means it's standard pressure and standard temperature. That's 25 degrees Celsius at 1 atmosphere, 780 millitorr, sorry. Make sure you 1 atm, which equals 780 millitorr. Had to make that clear. Do know that standard can either be stated as standard conditions, or it's stated at 25 degrees Celsius, and therefore you know you're in standard conditions. Okay? Just be aware of the terminology so you're not confused when you see something like this and you're like, what do I do? All right, number 1, let me pull up my pen. Number 1, we're going from graphite and chloride to tetrachloride, and this is already telling us the enthalpy. All right, so it's telling us to calculate system surroundings and the universe entropy changes. Cool. And it's telling us that the standard entropy analyses are needed, and we're going to get them from a graph that I, of course, don't have. I've already plugged them in, and I got them from a graph. You will be using them from a graph. And I first start off, I like to do the system first, because system is reactants or products minus reactants, and I take the sum of them. And I like that because for me, that one gets out of the way really quickly. I always do universe last because obviously universe is surroundings plus systems. And I like to do the surroundings second because I don't know why, but I find when I like to read this in a line. So this obviously has the reactants and the products, therefore system first. This then shows the enthalpy, and therefore the surroundings second. Anyway, back to the main gist. I take the sum of the products. Again, this is at standard, so I'm going to use that table, and I'm going to subtract it from the reactants. Remember, it's the sum of the reactants, and I have 2 reactants here. So notice that I've subtracted these added together, and I'm going to get the entropy of the system. Again, I'm going to, for the surroundings, take the change in the enthalpy, which is given to me, divided by the temperature. Because we're at standard, that means that it's going to be 298 Kelvin, aka 25 degrees Celsius. And then I'm going to change that into joules because my entropy is always in joules, and also because when I'm adding them together later, I want them to be in joules, but the enthalpy was in kilojoules. So I got to make sure that everything is in the same units as I was saying before. So then I get my surroundings is going to be 503 point something, and then I'm going to add them together to get the universe. Again, simple maths, please put this in a calculator, please. All right. Now we go on to number 2. Number 2 is nice because All we got to do is know that one formula that relates Gibbs energy to enthalpy and to entropy, and we're good. So it's saying this at 298 degrees, so this is actually at standard, but it doesn't say it's standard pressure, so I assume that's why in this question on the exam, they don't put standard signs. And all we got to do is know this equation. It's the golden equation. It relates everything to each other. Remember, though, these are all without the dot or the zero, so the standard part. But if I put this here, then they all have to have a standard. You can't have just one standard. All right. Now, I know that because the delta S is given in joules per Kelvin, but the other two are given in kilojoules, I'm going to need to either multiply this by 1,000 and later on make sure that Gibbs is in 1,000, or I'm going to need to divide this by 1,000. I like to make everything into kilojoules because Gibbs is usually given to us in kilojoules. So I'm going to take this in kilojoules, subtract the temperature, again, looking at my thing, multiplied by the entropy times 1 divided by 1,000. Cool, and that's going to give me my Gibbs. This is positive, and if this is positive, that means that the forward reaction is not spontaneous, but the reverse reaction is, and because the reverse reaction is going to be negative 55. Also, this is because we know that Gibbs at 0 is going to be at equilibrium. So these are things to take into account when you're reading these values. I'm so sorry, my writing is absolutely atrocious. Again, forward reaction, positive, therefore that means that it's going to be not spontaneous in the forward reaction, but definitely spontaneous in the reverse. All right, number 3. So we're considering a reaction that's described below. I can see that already the trick thing here is I've got a 3 for this ethene, and that's going to turn to cyclohexane. Cool. This is hexene. Nice. And I'm going to use the data, and I see that already it's standard because, again, it says standard pressure and standard temperature. Wonderful. The other indicator is this tiny 0 at the top, but overall, this is a great indicator that I've got standard temp, standard pressure, so I'm working in standard conditions. Okay. So I'm going to use the data in the table. I don't have the table, but the table would be with you in your supplementary information. And I already know how to find the part of the reaction where I take the products, subtract the reactants, and this is the sum, and I'm so sorry it's not written that way. But what's nice is I think I didn't do sum because there's only one of each, but I meant to say sum. And that's 1 multiplied by the standard entropy of the hexane, and then subtract 3 moles, because remember there's 3, so don't forget your coefficients, multiplied by its standard entropy, and that's going to equal my change in the reaction. And then to find out if it's actually going to be spontaneous is I need to plug it back in, which is why I was given this wonderful enthalpy reaction. So whenever you're given the enthalpy and it's asking you to find the entropy, you can always assume then you're going to be using Gibbs, especially if it then also tells you the temperature. So then I'm going to plug it into my wonderful Gibbs reaction that we got from before, and I again subtract my use my negative 45 enthalpy, subtract the temperature, multiplied by the entropy I just calculated. Again, though, that is in joules. So I need to make sure that it's in kilojoules. So I'm going to divide that by 1,000, and I get 103 kilojoules. Because this is positive, that means this reaction is only going to be spontaneous in the reverse. Same as we just talked about. All right. Take a break. Go somewhere else. Come back. Pause the video. And here we go. Okay, number 4, methanol is formed from methane and water in a 2-step process. This is something that was worked on in your homework, but I think a lot of people didn't understand the mechanism behind it, and I had a lot of people ask me about this question, and the thing is in the exam, they'll probably just give you step 1 or step 2, but I wanted to go through both, especially because what they might do is give you the value for step 1 and then ask you to add it to step 2, so I just want to cover all our bases here. So the first thing we got to do is get the enthalpy and the Gibbs from the given entropy for step 1. So again, first things first is we got to find the what am I doing? I got to find the enthalpy, and the change in enthalpy, just like we did with entropy, is going to be the sum of the products. Remember, please don't forget the coefficients. Luckily here, the only one we have to worry about is this 3 for the hydrogen, but please be aware of them. Another one to be aware of is hydrogen gas has 2, but that's for the next step. And then subtract the reactants. Okay, so to do that, I'm going to look at my standard enthalpy formation values. Again, you're going to have that given to you, so don't worry about that. I just looked them up. I plug them all in, and I'm given my enthalpy. Again, making sure to note that I did put that 3 in there for the change in the hydrogen gas. So please please, please, please be careful with coefficients. And then for Gibbs, we know that we just take, again, standard enthalpy, subtract the temperature times the given entropy value. And when I plug all these things in, I get 141.9. All right, when is it spontaneous? Ooh, wait. This is 200. I didn't plug this in right at all. This is 200. I think I rounded something. Well, it was given to me. I just didn't plug it in correctly. So I'm just going to quickly plug this into my calculator. Whoop, 205.9, subtract 298, multiplied by 200 divided by 1,000. And that gives me 146. Oh, I see what I did. 146. Perfect. Okay. 146.3. Great. Okay, now I'm going to note that when I take the temperature divided by the entropy, but that entropy again is in kilojoules, it is going to equal 1,029 degrees Kelvin. And that means that step 1 was not spontaneous at 298 degrees, as we can see by the positive delta G value. But we can see that this temperature is much greater than the 298 degrees. So this means that step 1 will be spontaneous when you're greater than 1,029 degrees Kelvin, which is very hot. All right, for step 2, we just do the same thing we did, plug in our values, again, making sure that we take into account that there's 2 moles of our hydrogen gas in the second step there. And the standard Gibbs free energy, again, we're just going to take that enthalpy, I can't talk, enthalpy, subtract the temperature, subtract, oh, I've done it again. This is why we don't make things simple. I try to make them hard again for myself. Divided by, so if I go back through and take negative 128.7, subtract 298, multiplied by 300 divided by 1,000. This is what happens when you don't have help. Negative 200. Write this out. 218.1 negative. And therefore I know that negative 218 is going to be spontaneous, because this means that the Gibbs is negative, and therefore the reaction is spontaneous. Now, again, I take that enthalpy that I calculated, divide by my entropy that was given, but remember my entropy is in joules, and therefore I need to then move it into kilojoules, and I get 429 degrees. So step 2 is spontaneous at 298 degrees Kelvin, which is less than 429 degrees. We can see that. So step 2 is spontaneous at temperatures less than, again, a weird temperature, 429. Awesome. All right, the other thing I'm going to do then is for the enthalpy, I'm going to go back through and I'm going to make sure that what I do is I take my Gibbs given, and sadly here I've got wrong numbers for this Gibbs. So I'm going to go back, and I remember that my actual Gibbs that I got was like 140. Let me check my... This is what's so lovely about a TI-89, and the reason they don't let you have them is that we're going to do 146.3 here, which is added together because we're adding them together for the full reaction. So you just sum them together basically. My negative 218, and when I do that, I'm going to get a negative. Oh, I'm going to get a negative. This goes even further incorrect. Or sorry, not incorrect, but further math errors. 218, and that equals negative 71.7-ish there, kilojoules. Good. And again, because I have a negative value over here, that means the reaction is spontaneous at 298 degrees, because again, I have a negative Gibbs energy, and even though my delta S is negative, we always go by spontaneity based on Gibbs. All right, I will fix this when I upload the slides, but for those watching, thank goodness for calculators. Okay, Number 5, a reaction here has a standard free energy change of negative 19 kilojoules per mole. That's great. We know in kilocal per mole. And I want to know the equilibrium constant. So the thing that we have to know is that there's 2 ways to get Gibbs at standard energy. And there's one where it's Gibbs equals negative RT times the natural log of K. And then there's negative 2.3 times the gas constant times the temperature times the log of K equilibrium. So we got to make sure that we just keep these separate. So for this one, we're going to use this equation. Don't use the other equation. If you mix together the equations, you get different answers. So what I'm going to do is I want to get KEQ. So I'm going to try and get KEQ all by itself. And then I like to do this before plugging in any numbers, because plugging in numbers and then raising things to different powers can be a mess. So first things first is I flip sides here. So I'm going to basically multiply this side by Gibbs free energy and multiply this side by the log of KEQ, and they flip sides. Great. Then I'm going to raise this side to the power of 10 to get this KEQ out of the log. Then that leaves KEQ equaling 10 to the negative Gibbs free energy. Luckily, they tell us the free energy change, divided by 2.3 times the gas constant times T. So then this is me just plugging everything in. I wanted to remind you, again, this big thing about about units. R, that gas constant, that right there, that is in joules. Remember, you were given this free energy in kilojoules. And so that means that I'm going to have to multiply this by 1,000 divided by kilojoules to make sure that everything actually cancels out. Otherwise, there was no point in you doing anything, because you're going to get a completely different answer. Because look at all this stuff canceling out. Kilojoules cancels out. Moles cancel out. This is all leaving itself behind. It's wonderful. And then when I do all of that math, I get 10 to the 3.141, which equals 1,380. All right, last problem here. This is one on the homework that I liked a lot, and it is something that the exam likes a lot. And why? Because it's not only can you write the equilibrium constant, but can you then apply it to Gibbs? And it's a simple plug and chug thing. Again, this is the other way to solve Gibbs free energy. Like I said, negative RT times the natural log of K. So just remember, this one is, is negative 2.3 times times the gas constant times temperature times log of KEQ. So there's 2 ways to do it. And when I see KEQ specifically, I always go for negative 2.3 times R times T times the log of KEQ. And then when I see K, then I always use, where's my pen? When I see K, I always use Gibbs free energy equals negative R times T times the natural log of K. I wanted to write that in, and there we go. And so first things first is I note that I've got 2 A's and I've got 2 D's. And that means that when I'm writing out K, I do need to make note and therefore raise these to the power, raise these to the power of 2. And I'm going to get a K of 0.995. Remember to plug these numbers in correctly, not so much correctly in that you raise the right things to the right power, and also you put the products in the top and the reactants in the bottom. All right, my reaction, again, this is in joules. This has no units. Everything's going to be in joules. Units, Victoria, units. And it's going to be in joules because these all cancel out. And then you're going to get, joules per mole. Good, because that is unitless. And I plug everything in and I get 10.2175 joules per mole. Again, Gibbs reaction energy is always done in kilojoules per mole, so I'm going to divide that by 1,000 and I get 0.0102 kilojoules per mole. Okay, that's all for entropy. Please send me emails with anything else that you have. I will be having my office hours, like I said before, not only on your normal Tuesday next week, but I'm also going to be having them Sunday, and I'm also going to be having them Monday. So Sunday, 7:30, Monday, 7:30, and then Tuesday, 11:30 a.m. and 7:30 that evening. All right, guys, good luck. Happy studying. I know you've got tons of exams. Just take a deep breath. It's all going to be fine. Okay, I'll see you guys later. Bye.